Hello guys, welcome once again to our PIC assembly language programming video tutorials with the Bang Party. Today we will be looking at the timer 0 module. We'll look at what is timer 0, how does it work, and how we can make use of it in our applications. Right. Now, to get started with timer 0, we're going to use those three examples there. Now, let's get started right away. The first one says they write an assembly program to toggle an LED connected to port A2 every 250 microseconds. Now, using timer 0 interrupts, we need to toggle the LED connected to port A2 every 250 microseconds using timer 0 interrupts. And it says here, assume that we're using a 4 MHz crystal oscillator and we're using timer 0 in the timer mode. I'm going to explain what timer mode is, right, when it comes to timer 0. Now it means in our application we're using a 4 MHz crystal oscillator and then we're using timer 0 in timer mode. We need to toggle an LED connected to port A2 every 250 microseconds, and we must be using timer 0 interrupts for this timing purposes. All right, let's get started now. How do we achieve this using timer 0? Meaning we need to look at implementing timer 0 interrupts and using timer 0 to get that 250 microseconds so that we can toggle our LED every 250 microseconds on port A2. Right. Now, how do we use timer 0? What is timer 0? Right. To try and get started or explain a little bit on timer 0, let's look at what we normally know as our olden, so I should be using our olden analog watch, right? Where we have 3 needles, but I want us to focus on the second needle. And second needle moves every second. Let's assume we started 0. So it moves 1, and then later 2 to 3, 4, and so on up until it gets to 59. That's the needles, the second needle. Right. And now at 59, instead of going to 60, on the 60th second, it's going back to 0. On the 60th second, it's going back to 0. It incrementing minutes, and then the seconds goes back to 0, starting again at 1. Now, we know exactly that for that needle to move from one point to the next, that will be exactly 1 second. And then for it to move from 1 to 2, that will be exactly another 1 second. From 2 to 3, another 1 second. From 3 to 4, that's another 1 second right there. Right. And then up until it gets to 59. And at the moment it moves from 59 to 60, it's actually going back to 0. Right. So, meaning the 60th second marks a minute and resets your seconds to 0. Right. This will also look at it in terms of timer 0. But now in terms of this olden analog watch, we know that the interval here is always 1 second for the seconds needle up until it makes a revolution at the 60th second. But now, how does that relate to timer 0? Let's assume that's our timer 0. It also starts at 0 at the top. So it will start at 0, and then it will increment to 1, 2, 3, 4, and so on. And now our timer 0 stops or counts up to 2, 5, 5. Now that's the big difference, or that's the difference, the first difference between that second needle in the analog watch and the timer 0. Timer 0 counts from 0 up to 255. Now, when it goes to 256, just like the seconds goes to 60, when it goes to 256, it's actually resetting, it's going back to 0. So on the 256th count, it resets, it goes back to 0. And then we say here, when timer 0 changes from 255 to 0, on that 256th count, we say it overflows. Whenever it resets, it overflows. And now, when we talk about timer 0 interrupt, we are actually talking about timer 0 overflow interrupt, which happens every time the timer overflows. We say it overflows because the timer has a capacity of counting up to 255. And now when it has to go to 256, because it doesn't have capacity to count up to 256, it overflows and resets to 0, right? So we call this timer 0 overflow interrupt. When timer 0 changes from 255 to 0 on that 256th count, right? So now, our timer, like I said, the first difference is that our timer 0 counts from 0 up to 255, it overflows at 256, right? Now, how long does it take for timer 0 to move from one count to the other? There's a second difference there. Here, this time is programmable. We can program and select how long it takes for our timer to increment once. We can set that timing, right? And now this time we call it, call it the time per count, because we're going to count from 0 up to 256. But how long does it take each count? This time per count is what we can program, right? So from that 0 to 1, it will take the same amount of time, and then from 1 to 2, it will still be that time per count, which we will assign. And then same applies from 2 to 3, time per count. 3 to 4, that very same time per count, up until it gets to 255. Now, when it has to go to 256, it actually goes to 0. It overflows here at the 256th count, right? Now, how long does it take to make a revolution? It will be time per count multiplied by 256, depending on what that time per count is, right? So we need to find out now, what options do we have to set this time per count, right? Now, the question said, use timer 0 interrupts to toggle the LED every 250 microseconds. But now we need now to first find out what can we set as the time, and what is the length of the revolution, and how can we achieve 250 microseconds using this timer 0, right? Now, the rate at which your timer 0 runs, that is the clock source of your timer 0. When using timer 0 in timer mode, the clock source comes from F oscillator, the speed of the oscillator you are using, divided by 4. That's the speed at which your timer 0 is running, right? That's your clock source for your timer 0. I'll call it, let's say, FC, right? This is the clock source of your timer 0. So let me just say CS clock source. Now, the question said we're using a 4 megahertz crystal oscillator or any form of oscillator. We're using a 4 megahertz oscillator, and then we're using a timer 0 in timer mode. If we're using our timer 0 in timer mode, it means that the clock source is from that F oscillator divided by 4. The clock source for timer 0 in timer mode is F oscillator divided by 4. If timer 0 was in counter mode, the clock source was not going to be F oscillator divided by 4. The clock source will be a frequency directly connected to pin RA4. Pin RA4 on port A will be the clock source for your timer 0 if timer 0 is used in the counter mode, right? But this time around we're using it in timer mode, so the clock source for timer 0 in timer mode is F oscillator divided by 4, right? Hence we can proceed and say now, with our 4 megahertz, what will be the clock source? With our 4 megahertz, now our clock source is going to be that 4 megahertz divided by 4. And then that will give us a clock source of 1 megahertz. Right. Meaning our current rate, or the primary rate, the clock source for the timer 0, it is running at 1 megahertz speed. Now, how do we get that time from that 1 megahertz clock source? Now, that time, we call it time per count. So our time per count, if running from the clock source as it is, or dividing, or using it as it is, or dividing it by 1, our time per count is going to be 1 over that FC clock source. Right, and then that will give us 1 over 1 megahertz. That will give us 1 microsecond. Right, this is our time per count. Now, this time per count, I want you to realize something. Now, with timer 0, we said we can program this time per count. But now, if we get our time per count from the clock source, which is F oscillator divided by 4 in timer mode, now, and then our oscillator is 4 megahertz, meaning our clock source is 1 megahertz. We are running our timer 0 at the rate of 1 megahertz, and if that's the rate at which we are running it, the time per count will be 1 microsecond. But how is that time programmable if we can get it to be 1 microsecond? Can we change it to be something else instead of being 1 microsecond? And then the question is yes, because it's programmable, we can change it from being 1 microsecond. But 1 microsecond is the shortest or the smallest period that count can take. Now, if you want a bigger period, right, we will say, let's take this clock source, this rate, and let's make it smaller and smaller. Meaning we can divide this and say this clock source divided by 2 so that it becomes 500 kilohertz, or divided by 4. And now the value that we divide it with is called the prescaler. We can divide our rate at which the timer 0 is incrementing. We can divide it by 2, by 4, by 8, 16, up to by 256. Meaning we can slow down the rate at which our timer 0 is running if we want to achieve longer delays. Right. Now, currently, when we use that 1 megahertz, it means our timer 0 clock source, we are using it as it is without dividing it. Right. Meaning that 1 megahertz, we are actually using a rate of 1:1. We are not using 1:2, 1:4. That this ratio means we are just dividing our clock frequency by the value on that side. So if you want to choose a 1:1, first we must choose the watchdog timer rate, because that's the only rate, or that's the only block where we get 1:1, right? So how do we assign our rate to watchdog timer or to timer 0? You see bit 3 of option register. We are looking at option register there. Bit 3 of option register. When that bit is set, it says our prescaler is assigned to this table, to the watchdog timer rate. When that bit is set, and now when bit 3 is 0, it says prescaler is assigned to timer 0. Prescaler is assigned here. Now to get a 1:1, we need to assign prescaler to watchdog timer, and then bit 0 to bit 2 of the very same option register, the 3 bits, bit 0 to bit 2, when they are zeros, 0, 0, 0, and then your rate has been assigned to watchdog timer, it means you are selecting 1:1. And then we are going to use that clock source as it is. We don't further divide it. But once we start choosing 1:2, then we can assign prescaler to timer 0 and then work through this rate. Whenever we are using timer 0, we are only going to assign prescaler to watchdog timer for the 1:1 rate, because that's the one we don't have in timer 0. From there, we all have them in timer 0. We assign the rate to timer 0, right? Now, if we want to divide, like I said, if you want to divide the clock source, we can choose 1:2, 1:4, or 1:256, depending on what we want to achieve. But do we really have to divide it at this stage? Let's go and have a look at that. Now, we are saying when we get our clock source in the timer mode, our clock source will be f oscillator divided by 4, depending on what that f oscillator is. And for our example, that f oscillator is 4 megahertz, right? Now, this is our clock source, 1 megahertz. Now, we can divide this 1 megahertz further by 2, by 4, by 8, according to the prescaler table. Or we can use it as it is by assigning a prescaler of 1:1, meaning we are dividing it by 1, or we are using it as it is, right? Because when you divide something by 1, it remains itself. Now, if we use it as it is, we are going to assign a prescaler of 1:1, and our time per count is just going to be 1 over the clock source. And now that will be 1 microsecond, right? So it means now it takes 1 microsecond for our timer 0 to move from 0 to 1, another 1 microsecond, and now the revolution is going to be 256 microseconds, right? Now, our question said, write an assembly program to toggle an LED connected to port RA2 every 250 microseconds using timer 0 interrupts. Right, we want to use timer 0 interrupts to create a 250 microseconds delay, and then we toggle our A2 every 250 microseconds, right? Now, how do we achieve 250 microseconds on this timer 0? Now we know that each count takes 1 microsecond, and the revolution is going to be 256 microseconds. We just want 250 microseconds, not 256 microseconds. Now, remember, our overflow only takes place when it changes from 250 to 0, meaning on the 256th count. It cannot overflow at 250, right? But that's what we want. We want 250 microseconds, not 256 microseconds. So how do we ensure that by the time it overflows, that will have taken exactly 250 microseconds, not 256 microseconds? We will start it somewhere. That's the answer. How do we ensure that it overflows at 250, not at 256? It means we don't start counting from 0. Let's preset our timer to start counting from, meaning we load a value into the timer. It's the same as setting a stopwatch or setting your clock at the beginning. You give it power, you set the time. and then it starts running from the current time, not the default time it was at before you inserted the power or something. Now we need to set our timer to start at 6 so that when it overflows, that will be 250 counts, 250 microseconds exactly, so that we achieve, we toggle every time we get timer 0 interrupt, we go and toggle LED. Every time we get timer 0 interrupt, we go toggle an LED. But if the timer starts from 0, that will be 256 microseconds, not 250. So to get 250, we need to start at 6. When it overflows, we get 256 microseconds, and then that's a toggling time. And then after toggle, we always load 6. We always start at 6, meaning on our timer we will have a point where we set it to start at 6, and then when it overflows, that will be 250 counts. 250 counts when it overflows, when it gets here, that will be 250 counts. And then because each count is 1 microsecond, that will make 250 microseconds. And now every 250 microseconds, we toggle our LED and we load 6 again to the timer so that it always starts at 6. We load 6, it overflows at 250 because that will be 256. It will overflow at 250 counts. And then when it overflows, we toggle the LED, we load 6 again so that it does that. Right. Now, how do we do that in the program? Let's go and have a look. I have already created a small assembly program, basic instructions that you should know by now. When writing a program, origin, the reset vector OX00, go to start, then we are going to have our start somewhere here. At this stage, I want us to set up our outputs. Status RP0. We don't have any inputs according to the problem. It just says we need to toggle A2. So A2 is our output. So I'm going to make all of the pins output. They didn't say anything about trace B. I can leave it as it is, or I can also make the pins output as well. It doesn't really matter. Right. Now, I want to set up my timer 0. Looking at what we did, or what we looked at in terms of option register. Now, I want to assign a prescaler of 1:1 because that's what we did. We didn't further divide our clock source. We just use it as it is. So it means the prescaler that we're supposed to use is 1:1. I need to assign prescaler of 1:1 to my timer 0. And to get a prescaler of 1:1, that can only be achieved under the watchdog timer rate. It cannot be achieved under the timer 0 rate. So what do? I need to say bit 3 of the option register. Bit 3 of option register must be set. Prescaler assigned to the watchdog timer rate. The watchdog timer rate is this one because I want 1:1. I can only achieve 1:1 in the watchdog timer rate. So I'm saying bit 3 of option register, that bit must be set to assign the rate to watchdog timer. And now, what rate am I selecting under watchdog timer? The 1:1. Meaning, bit 3 is set, bit 2 is 0, bit 1 is 0, and then bit 0 is 0. So that is 1 0 0 0 0. That is 8 in hexadecimal. Now, the upper 4 bits, I don't really care about them. Not going to use them. Bit 7, bit 7 is about bit pull-up resistors. We're not using it. Bit 6 is about the edge, the interrupt edge, whether the rising edge or the falling edge of the interrupt, RB0 interrupt. For now, we are not using RB0 interrupt, so I don't really care about those two. I can make them zeros. And then timer 0 clock source select bit. Timer 0 clock source must be from internal instruction cycle. Now, this is when you set your timer 0 in timer mode, this clock source must be the internal instruction cycle. Now, the internal instruction cycle, the rate at which your instructions are being executed, it is that F oscillator divided by 4. That will be your clock source. So we need to choose here bit 5, 0 to use the internal clock cycle using the F oscillator speed divided by 4 is our clock source. If we make this bit 1, it means now our clock source for timer 0 is the input frequency from RA4. Right, that is the counter mode. If we make clock source 1, that is configuring your timer in the counter mode, counting the frequency on RA4. Right. Whereas when we want to use it in the timer mode, this clock source must be 0. This clock source bit 5 must be 0 to use the F oscillator divided by 4 as our clock source. Right. Now this is going to be 0. So this is 0, 0, 0. Bit 4, it's only important if you're using your timer 0 as a counter, meaning if your clock source is 1, if your clock source is RA4, whether you increment on a rising edge or you increment on a falling edge of that input frequency. Right. For us, this is irrelevant because we're using internal instructions. So I'm going to make it 0. So that is 0, 0, 0, 0. The 4 upper bits are 0. The 4 lower bits are 1, 0, 0, 0. So that is 0, 8. I'm going to move 0, 8 now into option register. Why am I doing this while I'm in bank 1? Because when looking at memory organization, our option register there is in bank 1. Our option register is in bank 1. So I'm going to do this while I'm in bank 1. I'm going to say move a literal value into W. That value is 0, 8. Move W to file, option register. And now I think I'm happy with what has to be done in bank 1. So I'm going to say bit clear file, status RP0. Right. Now, I said we want to toggle an LED connected to port A2. Now we made the whole of port A pins outputs. Right. But now we need to enable timer 0 interrupts, and we need to start with our timer at 6. So we can either start by saying, let's move 6 into our timer 0. Move literal to W, OX0, 6. Move W to file, TMR0. Now, that register there, timer 0, this register is a register that holds the timer 0 count. Right. Timer 0 will be running in the background, but that register is the one that will hold the count. So we use this register to set our timer at 6 so that when it overflows, it is 256, meaning it is exactly 250 microseconds later, and then we can toggle our LED then. But now, why are we moving 6 into timer 0 once we're in bank 1? Because timer 0 is found in bank 1, bank 0, sorry. We had to switch to bank 0 first by clearing status, and then we move 6 into timer 0 because timer 0 is in bank 0. Right. We had to set up option 1, option register, while we were in bank 1 because option register is in bank 1. We switched to bank 0. We can access timer 0, and we are loading 6 into timer 0 when we're in bank 0. Right. And I said timer 0 is a register that holds the count of our timer 0 module. Right. Now, the incon register. Let's look at the incon register. We can still access it in bank 1. So while we're in bank 1, let's look at the incon register, mainly because we want to enable the interrupts. We want to enable now the interrupts, so we're going to look at the incon register. We want to enable specifically the timer 0 interrupt. So let me see if we are going to have the incon register. Yes, here it is. We have loaded 6 into our timer 0. That's where we want to start. And then let's see bit 7, global interrupt enable. So if we want to enable timer 0 interrupts, this global must be enabled. Peripheral interrupt enable. At this stage, we're not going to use any peripheral interrupts. So this is going to be 0. So that's 1, 0. Now, timer 0 interrupt. Timer 0 overflow interrupt enable. We want to enable this timer 0 interrupt. So this must be 1. RB0 interrupt. We don't want to enable it. That's going to be 0. So we have 1, 0, 1, 0. In hexadecimal, that value is A. Right. The first upper bits, they make A. This lower bit, I can tell you, they already make 0. We are not going to enable the port beyond change interrupt. That's going to be 0. Now, initially, no interrupt has taken place. So we are going to initialize this timer 0 interrupt flag. Remember, the flag, it's an indicator that an interrupt took place. So because we're initializing it, no interrupt has taken place. All the flags, we're going to make them zeros. So this flag, we're going to make it 0. This flag RB0, we're going to make this other flag also. All the flags are going to be 0. So this 0, 0, 0. And we don't enable port beyond change. That's a 0. So we have our hexadecimal A0 to move into the incon register to enable our timer 0 interrupts. So I'm going to say here, move literal into W, A0, and then move W to file, int con. Right. And now that will have enabled my timer 0 interrupt. What else to do now? Nothing. We just have to wait for the interrupt. Main, go to main. Right. Just being in the main loop. This main loop could be doing something else in our application. But in this case, there's nothing to do. We just wait for the interrupt. We know that the interrupt will happen exactly after 250 microseconds because we loaded 6 into timer 0 before we enabled interrupts. And now when the interrupt takes place, what happens? The PIC jumps to the interrupt service routine. And then it does that by jumping to the interrupt vector. So we must have our interrupt vector here. So the PIC will jump to the interrupt vector, which is address 04. Origin 04. When it jumps to here, then we know that it has got an interrupt. So let's go to our interrupt service routine, which you can place where you want to. I'm going to place it right here. My interrupt service routine. What is it that I want to do there? I want to reload 6 because I got an interrupt. It means it has reached 250 counts from 6, overflowing at 256. What do I want to do? I want to reload 6 into my timer 0 module. 06, so that it always starts at 6 and then it overflows after 250 counts, which gives us 250 microseconds. Move W to file, TM, timer 0. I know that the timer 0 interrupt has taken place, so I need to clear the interrupt flag. So I'm going to be clear file, int con, the timer 0 interrupt flag in the int con register is there. Timer 0, that's timer 0 interrupt enable, timer 0 interrupt flag. Remember we said the flag is set automatically when the interrupt takes place, and the flag must be cleared in software. That's what That's why I need to clear it now. The flag is set automatically when the interrupt takes place, and it must be cleared in software. So be clear file TMR0 interrupt flag, right? Now what I've done here, I've reloaded 6, I've cleared the interrupt flag. I haven't toggled port A2. I need to do that. Move a value into W. 0x 04 exclusive or W with file port A, comma file. This is actually toggling port A2, right? Why is it doing that? The exclusive OR gate, when you exclusive OR anything with a 1, if you exclusive OR anything with a 1, what happens? It changes its state. If you exclusive OR a 0 with a 1, the result of 0 exclusive OR 1, that becomes 1, right? So you are exclusiving OR 0 with a 1, you get a 1. If you exclusive OR 1 with a 1, what do you get? You get a 0. So whatever you exclusive OR with 1, you change its state. So now I want to change RA2. I exclusive OR with value 4. I exclusive OR with value 4. What is that I'm achieving there when I exclusive OR with hexadecimal value 4? It means now hexadecimal value 4 means 04 actually. The first 4 bits are zeros. A7, A6, A5, A4 are zeros. And now A3 is 0, A2 is 1, A1 and A0 are zeros. So that this value in hexadecimal is 4, and then obviously that one is 0. So I'm saying on A2, this is A0, A1. A2 is exclusive OR with a 1. Whatever the value of A2, if it was a 0, you exclusive OR with 1, it's going to become 1. If it was a 1, you exclusive OR with 1, it becomes a 0. That's how I'm toggling that A2, right? Exclusiving it OR with that value, port A with that value, and then what is left, it is just return from interrupt. Now let me save and build this. No problems. And let's quickly look at the simulator, how that is dealt with. Now let me load the program. No longer working on interrupts. It's timer 0 now. So this is my timer 0 hex file. Start simulation. It's running way too fast, so let me run it slow. Run it very much higher. Our port A2 should be toggling. What did I do there? Move exclusive OR W with file port A, save into 5, return from it. What did I do wrong? Port A2 should be toggling. Okay, something is wrong here. I don't know why or what it is. Let me do this. I don't think this should be the problem. Move return to W. disabling analogs, but because I'm using that pin as an output, these analogs should not be causing the problem to AD-1. So let me just put that code for disabling analogs and see if that was not the cause of the problem. Load the new heads file, start simulation. Oh, apparently it was. So even if your pins are used as outputs, you still have to disable those analogs, because now my output is blinking after I've disabled analogs on that port A, right? So you see now, every 250 microseconds, our A2 is blinking. Our A2 is switching on and off at 250 microseconds interval. That's basically how we make use of timer 0 and timer 0 interrupts, right? Now, basically this means that every time an interrupt takes place, so I start off by loading 6 into timer 0 and then initialize or set up my interrupt. And now it's going to take 250 counts for it to overflow at 256. That will be 250 counts. And when it overflows, it generates an interrupt. And then when it generates the interrupt, I jump into the interrupt service routine, reload 6 into that timer 0, clear the interrupt flag, and toggle the LED, return from interrupt. Because I've reloaded 6, it starts counting again from 6. When it gets another interrupt, that's exactly 250 microseconds later, I go to the interrupt, reload 6, toggle the output, return from interrupt, right? So that LED is blinking at 250 microseconds interval, as it was requested by our example there, the very first one. Now, the second one says, toggle the LED every 2 milliseconds. The very same LED, but now we are toggling it now every 2 milliseconds instead of 2 microseconds. We now to do it 2 milliseconds. How can we achieve that? Let's go back to our timer 0. Now, on our timer 0 here, we said when we are using clock source and a prescaler of 1:1, our time per count becomes 1 microsecond and our revolution takes 256 microseconds, and we could achieve the 250 within 1 revolution. 250 microseconds. We can achieve it by starting from 6 and we overflow at 256, but that was 250 counts from 6, giving us 250 microseconds. But now we want 2 milliseconds. We no longer want 250 microseconds. We want 2 milliseconds. In one revolution will give us 256 microseconds, which is less than 2 milliseconds. We want 2 milliseconds in that single revolution. We cannot achieve 2 milliseconds in that single revolution if our time per count is 1 microsecond. We can change that time per count. But now, that time per count, we can change it by further dividing our clock source with the value in the prescaler. Now, whether we divide that by 2, or we divide it by 4, or we divide it by 8, or by 16, by 32, we don't really know at this stage what value must we divide our clock source with for us to get 2 milliseconds in one revolution. Now, how do we find out which value to divide with? How do we find out which value to divide with? Comes here. You calculate your clock source, F oscillator divided by 4 in timer mode, and then this is your primary clock source. And then this is when you are using a prescaler of 1:1, right? Meaning you are not dividing it, or you are just dividing it by 1. You are using a prescaler of 1:1. But now we want a prescaler value which we must use so that within one revolution we can get that 2 milliseconds. We need to calculate now that prescale. But before we calculate the prescale, what is it that we are supposed to do? We're supposed to know first how many counts will it take us to generate that 2 milliseconds. We will say the required, we will say now the required number of counts. Required number of counts is equals to the required delay divided by the time per count. Now this time per count, it is this one where our prescaler, currently we are using the time per count where our prescaler is 1:1, because we are going to use this 1 microsecond. Hence I'm saying prescaler of 1:1. That 1 microsecond we get it because we are using that clock source as it is. We divide by 1, we don't divide by 2 or 4 or anything, right? So our prescaler is 1:1 here. So the required delay, it is 2 milliseconds. So we have 2 milliseconds divided by the time per count is 1 microsecond. And now the value that we get there is 2000 counts. We want 2000 counts. Can we get 2000 counts? No, because our timer 0 counts from 0 to 256 maximum, right? So we cannot get 2000 counts unless if we do multiple revolutions. But we don't want multiple revolutions. If we can achieve the 2 milliseconds in one revolution, that will be preferable, right? We can still do it in terms of how many revolutions, it's not a problem, but preferably we should have that 2 milliseconds in a single revolution, because we can change this time per count. So we need to find out by what factor are we supposed to change this time per count so that we get 2 milliseconds in one revolution. Right, so let's look at how do we get that. We know that we need 2000 counts, right? But we have a maximum of 256. Our minimum prescaler that we need to use, our minimum prescaler can be calculated to be the required number of counts divided by the maximum possible count. That's the prescaler we'll have to use. That's where we'll find our prescaler. What is our required number of counts? This is the maximum possible count, 256. Right, for timer 0, that will always be 256. The required number of counts is 2000. We require 2000 counts, but we have a maximum possible count of 256. So by what factor must we divide our frequency? So that will give us, if we use a calculator, that will give us 2000 divided by 256. That gives us 7.8. Now, if it gives us 7.8, we go to the table. We go to the table and say 7.8. We can achieve. We can use the 1:8 prescaler, because we don't have 7.8 prescaler here. We only have 816, and even if the results were let's say we were 8.1, if the results were 8.1, that 8.1 is greater than 8. There was no way we could choose 8. We need to choose the next higher value. So if you have 8.1, you don't choose 8, you choose 16. If you have 8.7, as long as it's above 8, it doesn't matter by what small factor, you choose the next value. It would have been 16, but it is 7.8. It is less than 8, so I'm going to choose the 1:8 prescale. Right. Now, if we choose the 1:8 prescale, this means that we are saying this clock source is going to be further divided by 8. Right. So this is time per count when the prescaler is 1:1. Right. But now our time per count, first of all, what's going to change is this is the time per count from the prescaler of 1:1. But now with our prescaler as 8, this time per count is going to change. Right. This time per count, we're going to get it still from the very same formula, but our FC clock source has been further divided by 8. Right. So what we are going to have is first the change on FC, and then the change on the time per count. So our new FC will be further divided by 8. So our new clock source, or here I can say that with a prescaler of 1:8, is just going to be this F oscillator divided by 8. So 1 megahertz, not the F oscillator, the clock source divided by 8, right? And now from here we now get our time per count. Our new time per count, this is with a prescaler of 1:8. Now that will be 1 divided by this 1 megahertz divided by 8. So 1 megahertz divided by 8. So this is basically, mathematically speaking, 1 megahertz multiply by 8. Right. So we know that this one is 1 microsecond. So that is 1 microsecond. 1 divided by 1 megahertz, it's 1 microsecond multiplied by 8. That will give us 8 microseconds. Right. Now it means now our new time per count, it's 8 microseconds. Right? 8 microseconds. Now, if one count is 8 microseconds, how many counts do we need to get 2 milliseconds, which is what we want to achieve? We want to blink our LED every 2 milliseconds. If our new time per count is 8 microseconds, how many counts do we need to get 2 milliseconds? We do the very same calculation. Required number of counts is the required delay over the time per count. But this time around, our time per count won't be with a prescale of 1:1, but will be with a prescale of 1:8. Our time per count, prescale of 1:8. Right. So when we do that, then it means a prescale of 1:8, a prescale of 1:8 is what we need to put there, is what we need to put here. So this is the required number of counts, the required delay divided by time per count, but then this is with a prescale of 1:8, and now this will be 8 microseconds. Right. 2 milliseconds. So we have 2 milliseconds, 2 exponent -3 divided by 8 microseconds. Divided by 8 microseconds, what will that give us? Divide by 8 exponent negative. Wow, we need 250 counts. So 2 milliseconds divided by 8 microseconds gives us 250. Very nice. Ironic. All right. Now, it means we still need 250 counts, but our timer 0 overflows at 256. Even for 2 milliseconds, we still need to preload our timer 0 with a value of 6 so that our counts we have, they give us 250. But this time, knowing that time per count is 8 microseconds, no longer 2 milliseconds, no longer 1 microsecond, but 8 microseconds. Right. Now, how do we achieve that 8 microseconds time per count? Obviously, by choosing a prescale of 1:8. That's what we need to do when we configure our timer 0. We choose the prescale of 1:8, then our time per count will be 8 microseconds, and we need 250 counts to get the 2 milliseconds. So we need to reload 6 into our timer 0. Right. So let's do that in the program. Now in the program, how are we going to do that? We are going to change. Since we are already loading 6, it's fine. We need to change the value that we put into option register, because this value is the one that's going to set the prescale. Now let's look at what value must we put into the option register. Looking at timer 0, let's look at that option register. Now we do get a 1:8 rate under the timer 0 rate, so we will assign the rate to timer 0 table, and then the last 3 bits will be 0, 1, 0. But if we assign watchdog timer or the prescaler to timer 0, bit 3 becomes prescaler assigned to timer 0 module. Prescaler assigned here. Bit 3 becomes 0 because we want to assign it to timer 0. Bit 3 becomes 0, and then we have 0 on bit 3, and then we have 0, 1, 0. That is 2. So 0, 0, 1, 0, that is 2. So we're going to move 0, 2 into the option register instead of 0, 8. We now move 0, 2 into the option register. That will set the prescaler of 1:8, and the time now will be 2 milliseconds. Build that. Let's go here, stop this, let's reload, and now you saw the rate at which it was flickering. Now it's flickering much slower, right? Because the delay now is 200 and okay, the delay now is 2 milliseconds, right? Whereas before the delay was 250 microseconds. Let's look at the rate. That's the 2 milliseconds rate. You see that rate. If I change this back to 8, meaning 250 microseconds, quick build this, so you'll see that rate will change. That's a 2 milliseconds rate. Now that's a 250 microseconds rate. Right. So that's the significance of that prescaler value. Right. Although the code is the same, that value there makes a huge difference in terms of the timing and timer 0. Right. So now we have achieved now the 2 milliseconds question. Let's go and look at the next one, what that says. Toggle the LED every 1 second. Now we want to achieve the 1 second delay, right? Now, if we want to achieve the 1 second delay, how do we go about it? Going back to our timer module. Now, our required delay is 1 second, no longer 250, no longer 250 microseconds, no longer 2 milliseconds. It is now 1 second. Let's go back and see. When we were using a prescaler of 1:1, so that should always be our reference, the 1:1 prescaler. Our time per count was 1 microsecond, but our delay, our required delay our required delay is no longer 2 milliseconds, but it is now 1 second. So we have 1 second, not milliseconds. Our required delay is 1 second, and our time per count is 1 microsecond using a prescaler of 1:2. We always use our prescaler. We always do this initially with a prescaler of 1:1, so that we get the required number of counts. Now, if you say 1 second divided by 1 microsecond, that's going to give us million counts. We need million counts, 1 million. You can do that with your calculator, it's fine. So 1 second divided by 1 microsecond, that will give us 1 million counts. Now, we are required to have 1 million counts. But we can't really have 1 million counts with timer 0, because timer 0 only counts up to 256. So we need to calculate our minimum prescaler, where we say our required number of counts divided by the maximum count. Now, our required number of counts is no longer 2000, it is now 1 million. So we need 1 million counts. This 1 million, that I will do with a calculator. That 1 million required counts divided by 256. What do you get? 3906.25. This is the minimum prescaler we are supposed to use. 3906. But according to our table, we don't have such a prescaler. Our maximum possible prescaler is 256. So we are left with no choice but to use the maximum prescaler. Right, to use the maximum prescaler, first of all, what value are we going to move to option register? You see, this value is 7. And then the bit 3 must be 0 to assign the rate to timer 0. So this value is 7. 0, 1, 1, 1, that is 7. So we move 0, 7 into option register. We will have selected our prescaler to be 256. Let's do that. We move 0, 7 into our option register. That makes the prescaler of 256. That is sorted. Now, we still need to find out now the counts and all of that to achieve this timer 0 1 million counts. But now, because our prescaler is 256 and it's the maximum, the time per count with our prescaler of 256, so this is going to be sorry, we need to erase it first. With a prescaler of 1:256, 1:256, and then this will be 256 here instead of 8. Of course, this will be 256 as well. So that is that divided by our clock source divided by 256. And then this will say that 1 millisecond multiplied by 256. And then this will give us the 256 microseconds. Now, this means it takes 256 microseconds time per count. Our new time per count, it is now 256 microseconds. So to move from 0 to 1, it's 256 microseconds. From 1 to 2, another 256 microseconds. How long does it take to make a revolution? One single revolution, how long will that take? Because now 256. We're using the maximum possible prescaler. Multiply by 256 microseconds. What will that give us? This gives us, I will say, 65.536 milliseconds. I'm moving this 1, 2, 3 to milliseconds. That's 65.536 milliseconds. One revolution makes 65 milliseconds to say, right? But now we want a 1 second delay, not anything less, right? So if we can achieve that 1 second delay in one revolution, because we are using the maximum possible prescaler, we cannot go further than 256, and in that case our revolution can give us a maximum of 65 milliseconds. Now we are left with no option but to say, how many revolutions do we need to achieve 1 second? How many revolutions do we need to achieve 1 second? So we'll say the 1 second we are looking for, let's divide it by the time it takes for 1 cycle. The 1 second delay we're looking for, let's divide it by the time it takes for 1 cycle, and then that will give us how many cycles we need to achieve that 1 second, right? How many cycles we need. Now in this case, if our cycle takes 65.536 milliseconds, we're gonna say 1 second divided by that 65.536, that is in milli, so exponent -3. 1 second divided by that says how many revolutions. We need 15.25 revolutions, but remember, with a PIC we cannot get that point what revolution, we can only get full numbers. So if we take 15 revolutions, that won't be 1 second, but if you take 60, that will be more than 1 second. Okay, the thing is, if we take 15, there's no way we can get a 1 second. It will always be less than 1 second. But if we take 16, we can tune each cycle so that when they are 16, they give us 1 second. So we're going to choose a value of 16 here, and then to say we're going to have 16 revolutions. But if we are going to have 16 revolutions, how long should each revolution take so that 16 of them, they make exactly 1 second? So our number of revolutions, our number of overflows, or what we can say, our number of overflows, or our number of interrupts, will be 16. We need 16 interrupts, right, to get to that 1 second. But how long should each interrupt be? Now we are going to say, now if we're going to have 16 interrupts, and then with that 16 interrupts we want to achieve 1 second, how long should each interrupt take? Now the new time now per interrupt will be this required delay, which is 1 second, divided by the number of interrupts we are going to have, 60. Right. Time per interrupt will be 1 divided by how many interrupts are we going to have, 60. And then this one is actually the 1 second, the time that we want. Now if we say 1 second, say 1 divided by 60. How long is that? That is 62.5 milliseconds. Now each revolution must take 62.5 milliseconds, and we know that the maximum, or the time it takes, it's 65.536 milliseconds, but we don't want 65. We can achieve 62 in that 1 cycle. And if we have 62.5 milliseconds per cycle, and 16 of those cycles, they will give us 1 second, right? So now let's do it that way. How long will it take? Oh, where must we start for us to get 62.5 seconds per revolution? 62.5 milliseconds per revolution. Now, our required delay will be the 62. Now, our new required delay, going back to the formula, required number of counts. Now we are looking for the 62.5. We are using a prescaler of 1:256. Hence, we got this most. So now we are going to use a prescaler of 1:256. Our required delay is now 62.5 milliseconds. And what will this be? Right. Now, we are saying our required delay 62.5 milliseconds, 256 microseconds. What do we get? So we say this divided by 256 microseconds. What do we get? 244 counts. We need now 244 counts. 244 counts, which we can achieve because the maximum count is 256. So, but now it overflows at 256. We want it to overflow after 244 counts. So, where must we start? Where must we start so that when it reaches 256, that is exactly 244 counts? Where must we start? That we call it the offset. With the 250, it was easy because when we started 6, we are going to get 252, 256. It was an easy calculation. But from 244, if we want 244 counts, where must we start that? So that when we get to 256, it was exactly 244 counts. Where must we start? The easy way to think about it, or to actually get it, is to use the formula that says the offset value. The offset value, the value that we want to start at, is called the offset. The offset value, that's what we want to get. Now, our offset value is always equal to the maximum count, which is 256, minus the required number of counts. In this case, we have 256 minus 244. What do we get? 256 minus 244. You start at 12. So we are going to start at 12, and then when it gets to 256, when it overflows, that will be exactly 244 counts, right? But now remember, we still have to count how many overflows, how many interrupts, because this offset, it's for achieving only 62.5 milliseconds per cycle. We need 16 cycles, right? So let's go back to our program and say, we want to start our timer at 12. So 12 in hexadecimal will be C, right? Now we move C into timer 0. But we also need to count 16 times. So I'm going to load a value, move a value into W. That value, it is 16. Okay, let me put it in decimal as dot 16. Move that into a register, which I'm going to call it a temporary register. and I need to declare what temp is. Temp is part of the general purpose registers starting at address 20 in the memory organization. General purpose register. So I'm going to save the value 16 into temp initially, right? So I'm moving 16 and I'm saving it into a general purpose register named temp, and I initialize timer 0 interrupts, but I've started timer 0 at 12 there. You see, now when I get an interrupt, it goes to the interrupt. I need to reload 12 on that timer 0, clear the interrupt flag. But before I toggle my LED, I need to check, was this the 16th the 16th interrupt? Was it the 16th interrupt? Because I need 16 interrupts. Because I loaded 16 there, I'm going to decrement file skip if 0. Decrement file skip if 0. That file is temp. So I'm starting from 16, right? If that temp is not 0, I'm not going to skip, because the instruction says skip if 0, right? So I'm not going to skip if that temp is not 0, meaning it hasn't been 16 interrupts yet. So I'm just going to return from interrupt here. So return from interrupt. But if that temp is 0, it means I've decremented that temp from 16 to 0. That is the 60th count. And now it can come and toggle your LED, but I also have to reload that 16 again, so that the next time around we also wait 16. So move 16 into W, move W to file, temp, toggle your LED. And then when you return, the moment you decrement temp, temp has 16 now. It's going to start from 16, 15. It's only going to skip when it gets to 0. So this is our 16 for the 16 interrupts we need. For the 16 interrupts we need, as it is stated there, the 16 interrupts we need, right? So let's build this program, and now you will see that that rate will be much. I don't think we will even be able to simulate it, because it is actually going to take too long for simulation to show us the 1 second. So I'm going to stop this, load the program, and then start simulation. It's going to take too long. Even if I do ultimate, it's still going to take too long. To see the real time, you see on your OceanSoft, the real time is there. Once that thing changes to 2, that will be our second. See, when that changes to 3, so you need to consider this time almost 3. That's so when that changes to almost 4, that will be another second. So to 5, that will be another second. So now it is toggling at each and every second, because it's waiting for 16 revolutions before it toggles. Basically, that is timer 0, guys. And that is how you make use of timer 0. And remember, we did move 7 into here to set up our prescaler to 1:256, right? So that's how you make use of timer 0. We look at the option register, what prescaler value is, and we perform our calculations to get how many interrupts if we need more than 1, and what is the offset value that we must start at, that we must load into timer 0, so that when it overflows, it gives us the counts which are equivalent to the time we need, right? So that's how you use timer 0. Timer 1 is also used the same way as timer 0. Same principles apply, except that we need now to look at the timer 1 register. So when I click here, timer 1 module, when I click on timer 1 there, so this is the timer 1 section. Now timer 1 is controlled through the T1 con register, not the option register as it is with timer 0. timer 1 is controlled through the timer 1 control register, and timer 1 has a prescaler of a maximum of 1:8, whereas for timer 0 we can go to 1:256, right? For timer 1 we end at 8, right? Timer 1 clock source, we can still use the F oscillator divided by 4 if we use our clock source to be the internal clock here. So our timer 1 clock source can be the internal clock. Then we will be using the F oscillator divided by 4 as it was with timer 0. Or we can use the external clock, which is on RB6, right? It means you'll have to have a frequency connected to pin RB6 of your port A pin. Now, you can choose internal, you can enable timer 1, and you can also select the prescaler value that you want. The calculations, they still are the same, except that timer 1 is a 16-bit timer. It's like 16-bit, it's not an 8-bit. What does that mean with timer 1? Now, with timer 0, remember, we could count from 0 up to 256 because it's an 8-bit. But with timer 1, that is not the case. With timer 1, it starts from that 0, and then with an 8-bit number. So starting from 0, with timer 1, we can start from 0, we can have 1, 2, 3, 4, but for a 16-bit, that is no longer 256. That is 65,000. What is it? Where is it? It's here even. At FFFF. That is actually 65,536. So with timer 1, we can do that up to 65,536. That's when it overflows. It overflows at 65,536, meaning the last count before it overflows will be 65,535. When it goes to 536, it overflows. Now, the only thing, you still have time per count, that is programmable, just as it was with timer 0. It's just that with timer 1, the prescalers you have, you can use this clock source as it is after F oscillator divided by 4 if you're using the internal one. And then with timer 1, you can count from that 0 to 250 to 65,536, and then your prescaler value is 1:1 up to 1:8. You no longer have a higher possible prescaler value, right? But now, apart from that, the calculations we did for timer 0, they apply to timer 1. Exactly the same, right? So timer 1 and timer 2, I believe we are through with them, and you guys should be able to use timer 1 and timer 2, timer 1 and timer 0, sorry, in your applications. And good luck. Go and do some more examples and change the required delay. See if you can perform the calculations and see if you can get the code working. Good luck, guys.